Okay, good afternoon, everyone. We're going to get started. So my name is Pascal Poupart. I've been invited by Ali to give a guest lecture. I understand this is a course on deep learning, and I'll tell you about one type of deep neural network called sum product networks. And I've been doing some work now for about 2 years with some of my students on this topic. So I'll first give you an introduction to the topic, and then we'll get into some more depth with respect to some of the recent work that, at least here at Waterloo, we've been working on. Okay, so as I go, feel free to interrupt me and ask questions, so I want to make sure that you guys at least get the intro. There's nothing hard here, but, just want to make sure that everybody can follow. Okay. All right, so we're going to start with just what is a sum product network. Then we'll talk about how we can use them to do inference and some applications. So this will be the introduction, fairly high level. And then again, we'll go into more depth. We'll talk about the relationship to other types of probabilistic graphical models. So for instance, Bayesian networks. I'll talk about some algorithms for parameter estimation, and then as well how to turn them into online algorithms and distributed algorithms. And then we'll talk about dynamic sum product networks for sequence data. Now, I'm not sure how much time I'm going to have in terms of covering all of this, but we'll see how far we go. And then as long as you guys enjoy it, that's all that matters. Okay? All right, so sum product networks were proposed in 2011 by Pedro Domingos and his group at University of Washington. And then at a very high level, what these are essentially acyclic directed graphs where we have sums and products. So there's an example here. And then the leaves contain indicator variables or otherwise univariate distributions. And then so we can think of this in several ways. One view is that this is a deep architecture, and then I'll claim that this type of deep architecture has some clear semantics, and I'll explain later on why it has some clear semantics. But then the other view is that we can think of these types of networks as also probabilistic graphical models that can be seen as equivalent or otherwise alternatives to things like Bayesian networks and Markov networks. Okay, so I'll explain this in more details now. So if we take the view of deep learning, deep architectures, then it should be fairly obvious that we can view this as a deep neural network in the sense that we have different functions that are applied. And then normally in a neural network, we have some inputs. We take weighted combinations of those inputs, and then there's going to be some activation function that is typically nonlinear. And then so in this case, if we simply view the product as the activation function, so you see here I can take two inputs. I can have some weights. That gives me a weighted combination. And once I feed those weighted combinations into the product, this is where I get something nonlinear. And then so from that perspective, we can view it as just like any other neural network, but with the specific case that we only use products and sums. Okay? Now, the main advantage of sticking with products and sums is that there's going to be some clear semantics that I'll explain again in a moment. And this is in contrast to perhaps other types of neural networks that you may have seen where if they use the sigmoid function or hyperbolic function or rectified linear functions, then often these things are justified simply from the fact that they tend to give good results, or we'd like to have some expressivity, but it's harder to interpret. And also in some cases, it's also harder to obtain algorithms that perform well. In any case, this is simple, but then that'll be the main advantage, that there's some clear semantics. Okay, to explain the semantics, this is where it's useful to look at the second perspective, where we can think of sum product networks as just one class of graphical models. So graphical models have been around for a long time. It started in statistics back in the 1980s with Markov networks. And then in artificial intelligence, also in the 1980s, then Bayesian networks were proposed. And what those networks are about is the idea is that we have some nodes, and each node, the semantics are that the nodes are variables, and then the edges will encode correlations, which allows essentially to define some joint distributions with different types of correlations between the variables. Okay, so these types of graphical models essentially allow us to represent compactly and to reason in interesting ways about joint distributions with respect to many variables, and then we can view some of those correlations or get some intuitions about them based on the edges. Okay, so who's familiar with probabilistic graphical model like Bayesian networks and Markov network? Okay, and who has never heard about Bayesian networks and Markov networks before? Okay, so I need to make sure to explain this well then. Okay, so these networks, again, because they encode a joint distribution, now the main difference between a Markov network and a Bayesian network is that here we're going to have edges that are undirected, so they literally encode correlations where here if I have an edge between D and E, it means that those two variables are correlated and it's undirected. Whereas here, I'm not sure if it's clearly visible, but each edge has an arrow, so it's a directed edge. And then that means now that we also have correlations. In principle, they're also undirected, but the way we express them is through conditional distributions, where we say that a variable has a distribution conditioned on its parents. So the correlations are essentially expressed through conditional distributions. And so that's how there's a direction associated with each edge. Okay, so there's been a lot of work, and in practice they're used for all kinds of things in computer vision, in natural language processing, in data mining in general. And then the beauty is because of the graphical view, then you can get a sense of the correlations, you can get a sense of how things relate to each other in your domain. And then it also encodes some structure that you can exploit to do inference. However, the main caveat with those two classic types of probabilistic graphical model is that inference is complex. Okay, so here, the complexity of doing inference is sharp P. So who knows what sharp P means? Okay, I thought that might be something not so obvious. Okay, so in computer science, we've got different types of complexity classes. And complexity classes refer here to how much time or how much space it would take for an algorithm to complete. Okay, and here sharp P means that it is in one of the complexity classes that at the moment we don't have good algorithms for. Okay, so perhaps one of the better known complexity classes NP, non-deterministic polynomial, and then so for that class of algorithms or that class of problems, at the moment we do not have an algorithm that would be better than exponential time. So that means that usually we can't solve very large problems. Now sharp P is worse than NP, and then again we just don't have good algorithms. So that means if I want to do inference with respect to a network like this, then if the network is large and has lots of connections, in general, I won't be able to do the inference quickly. It may actually scale exponentially with the number of variables that I have in my network. Okay? So that's at a high level what this means. So in any case, people have been working with these models since the 1980s because from a modeling perspective, it's nice. It helps a lot in terms of visualizing things, encoding structure, expressing things that are natural in domains. But from a computational perspective, they're nasty. Although from a research perspective, they're great because you can write lots of papers about trying to improve the algorithms and making them faster. But in any case, still today in 2015, I mean, we don't have exact algorithms that are tractable because they're in the class of sharp P. Okay? Now, if we look at some product networks, they're different. What they represent is that every node is either a sum or a product. So what they really represent is a computation we're going to do. Not so much the random variables that are part of our distributions. So these guys here, the circles or the nodes are random variables, but here the nodes are arithmetic operations, either sums or products. Okay? So it's a different perspective. So there, with sum product networks, we focus directly on computation. And the nice thing is that if we want to do inference, I'll show you in a moment how, we can do this tractably. So it's in the class of polynomial time. So that means we do have algorithms that run in polynomial time for this. And in fact, I'll show you that we can do it in linear time. So if you give me a network, and then I can measure the size of that network in terms of counting the number of nodes, then the number of operations that a computer will have to compute will be linear in the size of the network, and I'll be able to answer any inference query exactly with that. So this is very nice, because then compared to the previous Probabilistic graphical models, then we know that we're working with something that is tractable. Okay? Now there's obviously a catch. Okay? So we can't get something so good without paying something. And the catch is that the models or the distributions that we can encode here that would allow us to do inference in linear time are really a subset of those that can be encoded here. Okay? So the catch is that there's some loss in terms of expressivity, but in practice, still this is quite expressive. So we can learn lots of sum product networks that can be quite large and will behave well in practice. Okay, any questions so far? Does that make sense to everyone? Yeah?
What's the actual difference between sharp P and NP?
Okay. Yeah, so, okay, to give you an example, if we think of logic, a canonical problem for NP would be satisfiability. So if you have a logical formula and you'd like to know how can I assign the variable so that I satisfy the formula, this is NP complete. So in other words, any problem can be reduced to that. Okay. Sharp P, a classical problem would be to say, if I have again a logical formula, can I count how many satisfying assignments there are? So it's more difficult, because it's not just saying, does there exist one, and then as soon as you find one, you're done. Now you have to count all of those that exist. Okay? Yeah, so that's the main difference. Okay, any other questions? All right, let's keep going. Okay, so now that I've briefly introduced sum product networks, let me tell you a bit more how we can use them to do inference with respect to distributions that have many variables. Okay, so here, in general, we're going to have a bunch of variables. I'm going to use x to denote those variables. And I've got here a little example that has just two variables. So it's a very simple joint distribution. Obviously, we don't want to restrict ourselves to joint distributions of just two variables, but just for the sake of an example, we'll start with that. Okay? So I've got two variables, x1 and x2. And here, what I'm going to do is, in the leaves, I'm going to put x1 and x2 to be false or true. Okay? And then my claim is that I can compute the probability that x1 is true and x2 is false simply by setting some values for the inputs and then doing a bottom-up pass in a way that will add up the entries going up and then multiply the entries and so on. And what will come out here will be the probability of x1 true and x2 false. Now to do this, I need to set the inputs correctly. And so what I'll do is, since x1 is true, then I'll set x1 to 1 and not x1 to 0. And then x2 is false, so I'll set not x2 to 1 and x2 to 0. Okay? Then I simply do the arithmetic operations. So for the first plus node on the left, so I've got 2 times 0 plus 8 times 1. So this is 8. Then I have 0 times 1 plus 1 times 9, so this is 9. Here I have 4. Then after this, I simply multiply the entries. So I have 36 here, 32 here. And then after this, I take the weighted combination. So I'll have 0.3 times 32 plus 0.7 times 36. Okay, so this will be equal to 0.3 times 32 plus 0.7 times 36. So in fact, okay, this number is not an actual probability. It's just going to be a number that's proportional. So I'm going to have to normalize the entries. Okay, so I have to divide by a normalization constant. And the normalization constant, in this case, I can obtain it simply by setting all the entries to 1. So, okay, let me see if I can erase. Yeah. Okay, so I'm going to redo the computation. I'm going to set all the entries to 1. And now I get 10. Here, this is also 10. This is also 10. Then 10 times 10 is 100. And this is also 100. And then, so this whole thing is going to give me 100. Okay? So then the answer to this query, what's the joint probability of x1 true, x2 false, is obtained in this fashion. Okay, so I essentially do 2 passes through the network. The first pass where I set the entries to match what the query is, that gives me my numerator, and then I divide by a normalization constant that's obtained just by setting everything to 1. Yeah?
So how did we set these weights like 2, 8, 1, 9, and in the topmost layer 0.3, 0.6?
Okay, well, we'll get to that. So this is where we have to do parameter estimation. Okay, so these weights here are the parameters of the network. They're essentially defining what the distribution is. And what we'll see in a moment is that we can estimate these things from data. Okay. Any other? Yes?
Is there any particular reason you only have 2 inputs to the product for each product?
There's no particular reason. So this is just a simple example. And yeah, so I can have as many children as I want for each product node or each sum node.
So traditionally, are your networks fully connected between layers?
Ah, okay. No. So there are conditions that I haven't talked about. So in fact, not every network gives us a distribution. So some networks can encode distributions, and we're going to call them valid networks, and others do not. And in that sense, they're going to be invalid. And we'll come back to this in a moment. Yeah.
Is it just for discrete distributions or discrete variables?
Okay, so no, we can have as well continuous variables. So in general, at the bottom, we just need to have univariate distributions, and then the variables themselves can be continuous. So for instance, if I had a Gaussian here, and I could have just a bunch of Gaussians at the bottom, this would give me a hierarchical mixture of Gaussians. Okay, any other questions? Yeah.
Or just to follow on his question, so it would just give you the density value, then you'd have to integrate over a number of different continuous values to get like a probability?
Yes, so yeah, so if you have continuous variables, you'd have to, if you want to answer a query, then yeah, you'd probably want to integrate out variables that would normally be marginalized. And then for the variables that you have evidence about, then you can set those at the leaf. So in general, when I set values here, it's equivalent to saying I've got evidence and I'm setting the values there. Okay. Yeah.
I didn't get one thing. How do you visualize this SPN? Like in Bayesian networks, they're easy to visualize. It's a conditional probability and then we keep on going down.
Yeah.
Like I couldn't get what's apart from I can solve in linear time. What's the advantage and how do you visualize this thing?
So okay, this thing is giving you a visualization of the computation you're doing. So it's departing from the traditional way of using graphical models that are used to visualize correlations. Okay, because here we don't see what the correlations are. We just know that we've got two variables, and I can set them to true or false or 0 or 1, right? But it's not clear from this really what are the correlations or what are the conditional distributions and all that. But in the second half of this lecture, I'll explain how we can convert a sum product network into a Bayesian network, and then it will become clear. Yeah. Okay. All right, let's keep going. Okay, so yeah, let's just do another example where this time I'd like to answer an inference query with respect to a marginal. So I don't want to compute necessarily just the joint distribution, but maybe just a marginal. So I don't know what x1 is. I'm going to marginalize it out, and then you'll see how we obtain this. Okay, so this time if we want to answer what's the probability of x2 false, what we can do is set, again, x2 false to 1. Oops. Okay, good. So we'll set this to 1, 0. And now for x1, because we need to marginalize x1, so we need to consider both when it's true and it's false. So I'm going to set both of them to 1. Okay? And then we do the same computation as before. So this will be 4. This is 10. This is 10. This will give us 40, 100. And then this will be equal to, I guess, 0.3 times 100 plus 0.7 times 40. And then we normalize again by the same normalization constant as before, divided by 100. Okay? Any questions? Okay. Okay, now if we want to answer a conditional inference query, the probability of one variable given another, so that's not only just the ratio of two queries, a joint and a marginal query, so you can just obtain that from the computation that we did before. Okay? So the conclusion then is that based on these examples, it should be clear that now we can answer any inference query in two bottom-up passes, and therefore the complexity of doing this is linear. Okay? Okay, so now let's come back to what does this sum product network represents, and what is the meaning? So I've kind of answered a little bit some of those questions, but here the sum nodes, beyond just indicating that we're going to calculate a sum, and the product nodes indicating that we're going to calculate a product, we can interpret them as follows. So whenever you see a sum node, intuitively it means that in the joint distribution there could be a hidden variable, and then that hidden variable is really going to allow us to encode a mixture of smaller distributions that more or less correspond to the sub-SPNs under each sum node. So this sum node, we'll see later on that we can convert it into a hidden variable. Okay? And then the product nodes, intuitively what they're really doing is saying, if I have a distribution here, this child, and then another distribution here, this child, and then I take the product of those two distributions, well, we often do this whenever we have a joint distribution that happens to factorize, whereas there's some independence between some variables. Okay, so we'll see in a moment that this is exactly what that means, that the product is really indicating that there's some independence, there's some factorization between some of the variables. Okay, so to formalize things a little bit, we're going to need a definition here. I'm going to define the scope of a node as the set of variables that appear in the sub-SPN rooted at that node. Okay, so to make things clear, let's just write down what is the scope of every node. So if I start with this plus node here, it has in its scope x2 because its children have x2. Then this plus node has x1 in its scope, and same thing for this one. Okay. Then if I look at the product node right above, they have here x1 and x2. And then this one also has x1 and x2. And this one has x1 and x2 as well. Okay, so these are the scopes of all the variables in our network. Now, we're going to say that the sum product network is decomposable whenever each product node has children with disjoint scopes. So here if we check, we have two product nodes. They have two children, and they happen to have disjoint scopes. Therefore, this product node is going to be called decomposable. And the reason why we call it this way is because it corresponds again to this idea that we've got a distribution where we happen to be factoring the distribution in a way where there's independence between the variables in this scope and then the variables in that scope. Okay? And then same thing for this product node. It has x1 here as a child, x2 here. So these are disjoint scopes, so it is decomposable. So now based on this, we can say that this SPN is decomposable because all the product nodes happen to have children with disjoint scopes. Okay, the other important property is completeness. We'll say that an SPN is complete when each sum node has children with identical scopes. So here I have a sum node. It has x1 and x2 in a scope, and I look at the children. They have the same scope as well, identical. Okay? And then for these plus nodes as well, they both have x1 as scope, and here also again x1. Here they both have x2, so all of those are complete. Now the reason for completeness is because if we want to interpret the sum nodes as some sort of mixture distribution, if you take the mixture of two distributions, well, those two distributions better be with respect to the same variables. Otherwise, how can that make sense, right? So you have to have two distributions with respect to the same variables. And so that's the reason for this notion of completeness. Okay, and finally, we can say that a sum product network that is decomposable and complete is a valid sum product network. Okay, so this is a sufficient condition. Now, there are some product networks that are not decomposable and they're not complete, but they might still be valid. However, in practice, it's nicer to just go for those sufficient conditions because then, again, there's like these nice interpretations with respect to independence and mixtures, and then we know that it's necessarily going to be valid. Yeah?
The definition of a valid SPN.
Okay, so a valid SPN is essentially an SPN that encodes a distribution. And what I mean by encodes a distribution is simply that if we run inference queries, as I explained before, we're going to get the right answer. We're going to get answers that really correspond to probabilities that add up to 1. Yeah. Okay. Okay, now there was a question before about the relationship to Bayesian networks. Let me just give you a brief overview and we'll come back to this in a moment. But at a high level, what we can say is that if I have a sum product network, I can always convert it into a Bayesian network as follows. I can take every sum node, turn it into a hidden variable, and then I can also take the nodes that refer to specific variables and keep them as they are. And then I will create links between hidden variables and my original variables if they happen to be in the same subtree. And then I'll be able also to create conditional distributions that I've represented here using a special representation known as algebraic decision diagrams. Okay, so I'll explain this later, but this is just a simple example that gives you a sense that this particular sum product network actually has an equivalent Bayesian network that would have just one hidden variable and two observable variables. And it's equivalent in the sense that here I can take the weights that are associated with each sum node, okay, and then convert them into values as well in these conditional distributions, such that I will really encode the same distribution here as in the original sum product network. Okay. Okay, so we'll go through some more examples in a moment for this, but let me keep on going to quickly just give you an overview of parameter estimation, structural learning, and so on. Okay, so yeah, the next step is if we'd like to come up with a sum product network, and let's say we have already the structure, we're just wondering what should the parameters be. The parameters of a sum product networks are always the weights that are on the edges right underneath the sum nodes. Okay, so every edge that's coming out of a sum node will have a weight, and then we'd like to learn or estimate those weights from data. So there's been quite a bit of work on parameter estimation. Perhaps two of the most popular algorithms are expectation maximization and gradient descent. And I'll explain in more details later how we can essentially implement those algorithms. Okay. But basically, we can maximize the likelihood of the data to essentially find what would be good parameters, either by gradient descent or expectation maximization. Okay. The next question is, if I look again at this example, here I was just estimating the parameters given a structure, but where does the structure come from? Okay, so we'd like to have some algorithms that can also take as input some data and then can design the structure, give us a graph. So for this approach, there's also been a lot of work. In fact, Ali and some other people here have done some work on structural learning. I'm not going to review that work. I'm sure Ali can do a better job than me at explaining this. But at a high level, what many approaches share is that they will essentially create some nodes by clustering the data and create product nodes by partitioning some variables. Okay? Just to give you a high-level idea of how this works. Okay, so let me just draw something here. So again, if I have my data, here I'll have instances and the variables. One way of doing structure estimation or structural learning is that we're going to partition the variables and we're going to partition the data in such a way that will give us those sum nodes and product nodes. So here we can start with either the sum nodes or the product nodes. Let's just say that for now I'm going to start with creating a sum node at the top. Then what I can do to create this sum node, because this sum node I can interpret it as really being a mixture, then often we can think of mixture in the context of clustering, where if you have some data, you'd like to have part of the data explained by one distribution, part of the data explained by another distribution, and so on. So then coming up with a sum node can be thought as essentially clustering in the sense of partitioning the data into different subsets. So here I could use my favorite clustering algorithm, and then I could partition my data, where perhaps those on the left side of this bar that I just drew could be associated with one distribution. So this will give me a subtree here. And then maybe I draw another bar, and then I'll have two more children. Okay, and then they would correspond to different subtrees. Okay, so some algorithms proceed exactly like this. So they partition the data into three groups that are going to be associated with different sub-SPNs. Then typically after a sum node, you want to introduce a product node. So let's say that here at the root, we want to put a product node. Now a product node is going to correspond to partitioning the variables. So what I can do now is that this sub-SPN corresponds to this data, but now I'd like to partition the variables. I'm going to essentially introduce some lines horizontally to partition. So perhaps I put one line here and then maybe another one here. And then that means I'm going to have 3 children, okay, like this. And now you see each child is associated with one part of the data and the variables. So I'm essentially partitioning like this, and I keep on going. Okay? Yeah?
When you decide on clustering, what kind of, do you mean like k-means clustering? If I try and find...
Right, so yeah, so this is where there's lots of ways of doing it. So k-means is an obvious one. Some people have also used EM. Yeah, pretty much any clustering algorithm can work. Because all you need is just a way of partitioning the data. So it could be mixtures of Gaussians. It could be, yeah, any algorithm. Okay. Yeah, and then for partitioning with respect to the variables, the idea is that, again, when we partition, if we want to satisfy the decomposability property, we'd like the variables that are going to be associated with this sub-SPN to be independent of those here, independent of those here. So what I can do is I can take my data here and try to see in my data, are there variables or subsets of variables that happen to be independent or close to independent of each other. Okay, so you want to run essentially some algorithm that will measure correlations between those variables and then just partition them. And again, there's lots of ways of doing this. You can use pointwise mutual information and other statistical tests for doing that. Okay, so that's how you would obtain this. And then you would do this for every part. So like here, I would also introduce a product node. Maybe this one just has two children, because maybe I just partition it this way. And maybe this one here also has just 2. So I'll have my partition here, and then I would keep on going. Maybe for the first one here, I partition into the instances, which means I'm going to put a plus node, and then there will be 2 children like this, and so on. Okay? So that's at a high level how this works. Okay?
So you keep on going until you have like one element at the bottom?
That's right. So yeah, this algorithm would work, and then, I mean, you would stop when either you just have one instance, so you can't partition it further, or you just have one variable, and you can't partition that further.
At the very end, at the very least, do they all have to be on the same level?
No, so the height of different sub-SPNs could be different. Yeah, so there's no reason why they should all be the same.
So on the, all the columns here when you see instances, those are just vectors we have with known values of all the variables. So one instance would be x1 is equal to 1, x2 is equal to 0.
Yes.
With associated x1 not and x2 not.
Well, so every variable would be associated with a value. So yeah, here I guess I didn't give a concrete example, but when I say an instance, right, it means a joint assignment of all the variables. So if I have x1, x2, x3, and x4, perhaps this one is true, maybe this one is false, maybe this one is true, and maybe this one is true. So this would be one data instance.
And you explicitly encode x1 not, x2 not as well? Is that part of this matrix? Because if your variables include both.
Well, when I write x2 is equal to false, that means x2 not. Yeah. So does that answer your question?
Yeah,
Yeah.
you're just like in your tree where you have x1 and x1 not as 2 independent inputs.
Oh,
in order to
okay.
answer relational queries. You've done the same thing here explicitly.
Typically, I mean, the data would be stored in a way that's independent of the algorithms, and people would not actually put both x2 not and x2 true. So they would just put one because the other one is just follows from the first one, right? So like this could be one way of representing this, okay? And then, yeah, so this is one basic algorithm that I described. It was actually proposed by Pedro Domingo's group again. It's called LearnSPN. There are many other variants. Ali's group has developed one based on singular value decomposition. And well, I guess I should let him explain at some other time. Okay? I'll just leave it at that. Yeah.
Sorry, I still have more questions about this. So you're going to be clustering the instances and the variables, because basically you just want to have as a sparse representation as possible. You're not going to encode parts of your tree where you don't have any data for those variables. Is that part of it?
So, yeah, the tree here can have any shape. So some branches may be sparse, some other branches may be quite bushy, right? And it will really depend on how correlated the variables are, and then also how many clusters there really are in the instances that need to be represented. So the more clusters you have to form, then that means the more children a sum node will have. And then when you partition the variables, if there happens to also be a lot of independence, then you might have a lot of branches. So I'm not sure if I'm answering your question, though.
So I guess my question is, when you're clustering a matrix, like when I think of matrix clustering, normally we want to get in the end a matrix which is highly diagonal.
Oh, okay.
Right? And so what does a diagonalized clustered matrix of the variables instances matrix represent?
Right. Yeah, because if it was a diagonal matrix,
you're reordering things such that your variables that seem like they have correlated instances are next to each other in your ordering of them.
yes.
Which means that you're going to have a sparser tree structure. Is that kind of what you're trying to do? When assigning structure, you want to say that whenever I have instances that are like, they should be in the same subtree?
Yes. Yeah, so yeah, I think you're right that if somehow the data was such that we could associate a subset of instances with a specific subset of variables and then make some kind of block diagonal, then I believe we should be able to obtain a tree here that would not be very deep nor very large, because we might just need one sum node and then a few product nodes. It might just, like the size of the tree might just be linear in the number of blocks that you end up with. Yeah, but I don't have good intuitions about this. This is a very interesting way to think about it. Ali, do you have any thoughts about this? Because I know you've worked on that problem more than me. So.
Yeah.
Okay, you're talking near the bottom.
Yeah, right.
Then,
Yeah.
okay, let's say here.
Yeah, like one node there, one leaf there, that would have how many variables exactly?
Oh, okay. In a leaf, there would typically be just one variable. So we do this.
I'm talking about all the way down.
Oh, okay.
At that point there.
Okay, like let's say here. Yeah, so there would be a subset of the variables that come from, like, because I've got a product node here, I would be partitioning, right? So here, this particular leaf corresponds essentially to this region. So that means I'm only considering this subset of the variables.
And those are uncorrelated with any of the others?
Yeah, the idea is that in that data, when I only look at those instances here, right, then those variables would be independent of those and also independent of those. Although in practice, I mean, when I say independent, it might be more like approximately independent.
Uncorrelated number.
Yes, yes. So yeah, we'll talk more about this later. So there's a notion of normal SPN, and that's exactly that, where we want to essentially collapse certain nodes that are not needed, and you should really just have an alternation of sums and products. Yeah. Okay. Let's keep going. Okay, so now what I'll do is I'll talk about one particular application. So some product networks have been applied in the context of image completion, activity recognition, language modeling, and speech modeling. I'll just focus on language modeling, but in any case, I mean, it can be applied to many things. Just to give you a sense of what can be done and how good they are. Okay, so for language modeling, here the problem is, let's say we have some words in a sentence. Okay, I've got so I've got a sequence of words, and I'd like to predict the next word. Okay, so for instance, could be I like, and then we're wondering what's going to be the next word that will come. Okay, and let's say that we've got a set of documents, a corpus, okay, and we'd like to be able to predict what the next word is going to be. So this is a classic task in language modeling, because if you can already predict what the next word is likely going to be, then that helps a lot with machine translation. It helps a lot with understanding the language, because you might just be able to guess already what is going to come next and so on. Okay, so that's a classic task. And here, this would be word I. This is word I minus 1 and word I minus 2. And then we can formulate this problem as what is the probability of word I given word I minus 1 and word I minus 2. Okay? All right, so a lot of people in natural language processing looked at this. The classic way of modeling this is using an n-gram model, which is exactly what I wrote here, that we can estimate from the data distributions where I look at the past n words. So n-gram means that I look at the past n minus 1 words, okay, to predict the nth word that comes next. Okay. Okay, so the simplest way is to actually have just a discrete distribution over the entire dictionary of words for what might be the next word given the previous words. The problem with this is that, you see, if we consider the English language, especially now, I guess with short text messaging and so on, people tend to invent new words all the time. So there might be hundreds of thousands or millions of words. So this variable could have hundreds of thousands or millions of values, this one too, and this one too. So now if you take the cross product of the domain of all these things, right, it becomes something fairly large. Okay? And most of it is going to be sparse, because you're going to have only a few combinations that will occur in your corpus. Okay, so in any case, you'd like to be able to estimate this from data, and then instead of having a flat distribution or a distribution that would literally enumerate all the possible values, can we encode this in a way that would be a little more structured? And then this work here, which was published in 2014 by Chang and some co-authors, so I was not involved in that, they essentially proposed to use a sum product network to do that. Okay, so here they have some values at the bottom, and then those values indicate for a sentence. A 1 indicates that a word is present, 0 means that it's not present, and so on in the sentence, or at least in the n minus 1 previous words. And then you just feed this to the network, and then you can compute the probability for the next word. Okay. In their case, what they did is they use a fixed structure. So the structure was not estimated from data. They essentially designed it by hand, and this was the structure that they used. Okay. So you can see that there are various sum nodes, and then product nodes, and so on. Okay. Now, the weights, which are the parameters of the model, were estimated by discriminative learning, where they were trying to essentially maximize the probability of the next word given the previous words in a data set. Okay? Okay, and here are some of the results that they obtained. So they did it with considering the past 3 words, past 4 words, and here I believe this is a weighted combination of those 2 models. Okay? So they measured perplexity, which is related to the likelihood of the data, where here lower is better. So perplexity is some sort of measure about how surprised a model is to see a word. And then if the likelihood of the word is low, then essentially it'll be very surprised, and the model is good whenever it's not surprised because it would expect the word to come next. Okay? So here, lower is better, and again, you can think of this as sort of like the inverse of likelihood. Okay? So you'd like this measure to be as low as possible. And then so their model essentially ended up beating the other models before, and then they compare to this one here. Nerzini is a classic model that for a very long time was the state of the art, but nowadays neural networks are better, and then they've compared to a feed-forward neural network, a syntactical neural network, a recurrent neural network, a latent Dirichlet allocation model with an augmented recurrent neural network, and essentially did better than all of those. Okay? And then the second column is when they take these basic models and essentially combine them by taking a weighted combination with the Nerzini model, because that was a classic one, and often if you create an ensemble, it gives you better results. Okay? So by combining them, then the results are even better. Okay? That's a good question. Okay, so in general, I guess with a sum product network, what happens, if I just go back, is that you have here some general function approximator. Right? You can think of this as really computing some sort of polynomial in the input, because I'm either adding up stuff or multiplying stuff, so that gives me a polynomial, right? And here, if I design my polynomial to be expressive enough, I can actually learn polynomials that might match this task quite well. Okay, so there's some good expressivity, and then because it's still simple, we can do the training well, and as a result, it tends to give good results. Okay, other models, if I just go back, might not be as expressive, although the neural networks here are just as expressive, if not more expressive. But in some cases, like depending on how the recurrent neural network is trained, it might lead to some divergence, so there's some issues there. I actually do not know really the details, but in any case, that might be one explanation.
So these weights that we assign, they correspond to the frequency of the word appearing together with the other word inside the corpus?
Oh, yes, yes. So that's essentially what it's capturing. Yeah. That the corpus, there were sentences before where some words co-occurred, and then when it's predicting the next word, it's based on this co-occurrence information. But this co-occurrence information could have, positive correlations and negative correlations. Like if I see this word before, maybe it means this. Unless I see this other word, then maybe it means that, and so on. And it can be complex, and that's why this could do well. Okay. Well, so here the clusters, in some sense, are already decided by the structure. Okay, so here they actually hand-coded the structure. They did not run a structure learning algorithm. Okay, so they did not do the clustering and the partitioning that I explained before. Okay, so this was hand-designed.
So they just took and say, okay, I assume there is 100 clusters, and then they ran on it, and it worked.
Right, so yeah, so here this means we're going to have 3 clusters for the data. Then in one cluster, we're going to partition the variables into 2 groups, okay? And then in this partition here, we're going to then further partition the data in a certain way, and so on, okay? In the paper, they actually give some intuitions about why they designed their network in this particular way, although honestly, I did not follow their intuition, so I can't relay it to you. And very often in this type of work, it's more an art than a science at this point for designing structures. Okay? Yeah?
So there are 2 layers of sum on the top of each other, like H and M are
Yeah.
sums layer?
Yes. Yes. So that's how it is. And then, it doesn't have to be this way. They could have collapsed this into one layer. Okay, the problem is I don't remember again what are the details and the justification for this particular network, but yeah, we'd have to look at the paper for that.
Do you mean that the very bottom layer of the actual input word vectors was manually clustered for the whole corpus?
No, the input is simply the bag of word models. So you have a sentence, and then whenever a word appears, then it's going to be 1. Whenever it doesn't appear, it's going to be 0. So then essentially there's one variable per word in the dictionary, and then it's either set to 1 if the word appears and set to 0 if it doesn't. So here it's not something done manually. I mean, it's a computer that will just read the sentence and then convert that to a sequence of 1s and 0s. Does that make sense?
Sorry, I don't mean that part. I mean, so the H1, do you see how like V,
Oh, okay.
so that structure was made manually by
Yeah.
manually clustering the entire corpus?
No. So the structure was made manually simply by saying we're going to put a sum node here, and then we're going to link it to these entries. And then the clustering of the data doesn't really happen. Like nobody spent time doing some clustering on the data. That would normally be done if you're trying to come up with the structure automatically, but if you're coming up with the structure manually, then you just go straight and put a sum node here and you're done. Okay. So what happens is that then the algorithm will essentially try to fit some clusters more or less based on this structure, but it's not done manually. Yeah. So in any case, I mean the parameters are learned by maximizing likelihood, and we're going to talk about this next. Yeah.
Do they factor in linguistic rules into the model? Like, for example, adjective nouns usually follow together or something like that?
None of that. So this is the interesting thing that computational linguistics, natural language processing, 20, 30 years ago was heavily influenced by linguistics. Now there's been less and less of that. It's more data-driven and then more corpus-based. And this is an example of that where there's actually no linguistics at all. Yeah.
So these results are influenced by the corpus that you are working on.
Yes.
Right. So if it is sports literature, then the outcomes may be different if it's like a Shakespearean literature, right?
Exactly. Yeah. So then it allows you to essentially tailor your language model to the domain that you want to use it in, but then with the caveat that you can't quite use it in other domains, or at least it won't perform as well.
But it's interesting. The results are like, at least what they show is better than these recurrent neural networks.
Yeah.
More hyped.
Sorry, more what?
More hype about those.
Oh, okay, more hype. Yeah. Yeah.
So if you're adding the learning component to this model, so the system encounters something it didn't expect, how can you integrate it into this tree?
So here, if we're talking about parameter estimation, and then we just get more data, like you have a new sentence, and then the model was not able to predict the next words well, then you can just treat this as another data point for training, and then retrain the model. So you could do that. If, on the other hand, you want to do structure estimation and then change the structure based on that, I'm not aware of a method for doing this, so that would be a great question. Yeah?
So this G is product between, supposed to be product between two things, right? But
Yeah.
it's not visible from here, is it?
So here this is a little weird, but they also have this thing where they take the product of the same node. Okay, so they essentially square the result. Okay. Yeah. Okay, so this now concludes the first part. Basically, I just gave you an intro to some product networks, and we can view it as a deep architecture. Hopefully, you You can see that there's some clear semantics associated with that. And then we can also view this as a probabilistic graphical model, but it happens to be tractable, which is very nice. And what I'll do now in the second part is talk about some recent work that my group has been doing. So I'll explain in more detail how we can take any sum product network, convert that to a Bayesian network, how we can do parameter estimation in the framework of signomial programming, how we can do online parameter estimation, and also use sum product networks for sequence data. But let's take a small break.